Well, good afternoon, everyone. Welcome to the session. Before we get into the tutorial questions, are there any questions or comments, anything in particular you'd like me to go through, noting that this is likely to be our last class discussion before our last test. Okay, if not, let's go straight into it. So I'm just going to share screen here. Okay, please go ahead, Alyssa. Please remember to unmute yourself. Okay, so the question is on the chat, and the question is for the test next week, do we have a similar format as for test one? Yes, it will be a similar format. So about 50% multiple choice questions and those 2-mark type questions, and then there will be some questions that need a bit more development. So slightly longer multiple choice questions mixed in there. And then in a separate section, there will be more development. That's the plan right now. If there's any change to that, I'll let you know. But yeah, I'm happy with that format. So I plan to go ahead with that. Yeah, any comments on that? Yeah, so the question is, will the test also be 3 hours again? I'm not too sure. I felt 3 hours was too much last time. 3 hours is probably too much time for that test. Yeah, although I can't really imagine you asking for less time, but yeah, maybe you can tell me 3 hours was too much time, right? Okay, 3 hours was perfect, is the one message I've got. Yeah, so another comment, 3 hours was good. We had enough time to check our work. Yeah, to me, this thing of time limits has always been a bit of an arbitrary thing. When you actually practice engineering, quite often you have a good few days to solve a problem. So I don't know, I don't really see the point of setting limitations. Although when we set these tests, we do try to actually keep in mind a certain time frame. So I did think all those problems were doable in less time, but if you look at the way we teach the course and so on, everything is about spending more time thinking about what we're doing. So I don't have a problem with giving as much as 3 hours to do those problems. Then if there are no further questions or comments of that nature, then let's get into it. So here we've got, we discussed this first question last time already. So we'll go through the questions. We can also go through the notes. So please let me know if you'd like to go through any of the theoretical development as well. So we'd developed E of theta. So we know that given a pulse tracer experiment and given a concentration profile that results, we know how to get the exit age distribution. We also know how to get the internal age distribution as well, and the mean and the standard deviation and so on. And then we talked about drawing out the E of theta and I of theta for different variants. So if your base type is the plug flow reactor, then a variant on that would be that some of the volume would be dead. Another variant is that perhaps there might be bypassing around that reactor. So we looked at and we looked at that for the CSTR, and we looked at different arrangements and so on. So, and again, the concept there was we imagined putting in a pulse of tracer, and we imagined what happened to that pulse of tracer as it traveled through. So those were the kind of mental crutches that we used to estimate for ourselves what the exit age distribution would be. And then always, if you have the exit age distribution, then you can go ahead and find the internal age distribution just through the established relationship between the two, which is like this. So it's 1 over tau. So I of theta is 1 over tau times 1 minus the integral from naught to theta for E of theta in theta. So this can always be used. There's no prescription on when you can use this relationship. It doesn't matter what type of mixing is in the reactor. You are always allowed to use this relationship to find I of theta. And of course, it relies on you knowing E of theta. So as long as you have a function E of theta, you can perform this integration and get I of theta. Just be aware that or rather, just understand clearly what we are doing here when we are talking about integrating naught to theta. So maybe let's try and sketch that out quickly. Where's my brush? Nope, that's not there. Okay, so if we have E of theta, so let's say we've got some function E of theta that looks something like that, whatever it is. And we want to integrate from naught up to theta, right? Of course, your axis here is theta, and this is a plot of E of theta, right? And so we want to integrate up to some specific value of theta because we want to know I of theta, right? So to find I of theta, we can see we need this integral up to theta. So we construct this function through a series of values. So we substitute theta equals 0, theta equals 1, theta equals 2, and so on. So you choose a series of values of theta. And so that defines here's 0, that might be 1, that might be 2, and so on. So for each value of theta that we want to know I at, we have to go and reintegrate under E of theta. So if we want to know I of theta at 1, then you have to go and do this whole integration here. Then you take that area and then you put it in that part of the equation. So you get a number here, which is from the integral, and then you perform the rest of this operation, and that's I. And so each value of theta requires a new integral there. Of course, you can do this efficiently if you recognize that if you want a later value, so if you want the number at 2, then instead of going and reintegrating this part, you can just find the integral in this part and then add the earlier integral. So that's a more efficient way to do it. But in principle, you need to do this whole integration to get a single value here. Right, so just be careful that you understand what this means and what it requires us to do to get a number out. So anyway, that's what we do there. And then in the next question, we had estimated the volume fractions by using the definition of the space-time and the relationship of space-time with the mean residence time. So we know that the space-time tau, which is equal to V over Q, right? That is also equal to the average age. So theta bar for average age. And the average age is the integral over all possible values of theta. Integral from naught to infinity for theta times E of theta. Right, so if you have E of theta, so you see you can do many things if you have E of theta. So if you have E of theta, then you can just multiply theta by E of theta and integrate that function over all possible values. So again, if we have, let's say we have an E of theta like this. One second. So if you have E of theta like this, then we could go ahead and also plot theta as a function of theta, which is nothing but a simple straight line like that, right? So if we plot theta times theta, theta as a function of theta, it's a straight line, y equals x. and then you could multiply. So you could select values at corresponding locations. And so if you pick a number here, then you pick another number here, and so on. You pick a number here, you pick another number here. So you multiply this number by this number, and then you multiply this number by this number. And so you pick a series of values like that, and then you can numerically integrate this. And obviously, because E of theta is going to die out by some stage here, you can say, well, then I might as well only integrate up to this point. And so if you do that, you will end up estimating the average age. So that's your theta overbar. And then because we know the average age is the same concept as the space-time, then those are equal. So then we have a number for tau. And then if we know the volumetric flow rate, then we can estimate the volume. So that was the basis on which we calculated the volumes for each of the phases. And that's how we estimated the fraction of the stagnant liquid. So that's what we did in the case of this gas here. In the case of this liquid, we didn't actually integrate this because actually you can't, because you don't have decently specified numbers here. However, in this case, we took advantage of another property, which is if you can see that this curve is quite symmetrical, then if you understand what we mean by this average theta, clearly this is the average age in that system. And then just by inspection, you can see here that the average age in this liquid, in this vessel, the average age there must be 40, right? If all your fluid is distributed around this age of 40, then clearly it's just another way of saying that the average age is 40. So that's what we did for the liquid. We didn't actually integrate this. In the gas case, it's a little bit more complicated because now we have some finite numbers and it's clearly not symmetrical around this. So we had to, and see here, we weren't given a maximum value. We didn't have a number for this maximum point here. So in a way, this didn't look possible to do. But we then took advantage of another important property for us. So we have the property that, of course, E of theta, or rather the integral, if you integrate over all possible values of theta for E, right, this integral over all possible values, this must be a 1, right? Basically, we are adding up all the fractions of all the possible ages. So all that is going to add up to a 1 over there. So if that's the case, then we can figure a way around the fact that we don't have a maximum value here. So we know that E of theta. So what's going on? We know that E of theta is equal to the concentration of the tracer divided by its own integral. Apologies for that. I seem to have dropped the connection. Can you all hear me? Please use the reactions if you can hear me. Okay, thank you. Sorry about that. I don't know what happened there. So back to this, we were saying that we can estimate, we know that we can get E of theta by taking the tracer profile and dividing by the area there. So here's theta, d theta. Right, and so we are integrating under the area. Now, we don't know this number, we don't know this maximum point, but we can, clearly it's some constant. So let's just call that maximum point K. right? And so if we've labeled that k, then we can develop an equation for this line here. So we can say the function cg, or yeah, I've called it CT, so I should have said cg here. So cg, and this is eg. So we can say here that cg equals, and then it's going to be 0 for theta less than for theta values less than 6, it's going to be 0. For theta values less than 6, it's going to be 0. And for theta values more than 15, it's also 0. So that's one part of the function. And then the other part of the function, sorry, did I say 0? Should be 15. So for theta less than 6 and more than 15, it's a 0. And then when it's between 6 and 9, we can see it's a different function. So at 9, it's a value of k. So we can rewrite this using our linear equation as, we can write this as it's equal to, and then the gradient part, we would say k minus 0 divided by, and then at k, it's 9, and then at 0, it's 6. So 9 minus 6, and then times, so that's a ratio, and then that times theta minus, and then you just pick one point. So let's just take the 6 here. So theta minus 6, and then plus 0. And so obviously we don't need to write that 0 in here, so we can knock that out, and then we don't need this here. So this is just 9 minus 6, which is 3. So k over 3, theta minus 6, for theta between, and in this case, it's between 6 and 9. So this is for theta more than or equal to 6 and less than or equal to 9. And then it's also equal to, and then here we would say it's going to be 0 minus k divided by, so at 0, it's 15, and then at k it's 9. So 15 minus 9 times theta minus, and then let's just pick this point 15, so minus 15 plus 0. And then we don't need to write the plus 0, and then we can take that off. And then 15 minus 9 is obviously a 6. So that's the other function. And so this part is for theta is more than, or well, it needs to be more than 9. So more than 9, but less than 15, less than or equal to 15. Right, so it's a piecewise function, but now it's defined in terms of theta and in terms of k, which we don't know. But clearly, it's going to be linear in k, right? So if you consider values of theta just between 6 and 15, you are going to get a common factor of k here. Yeah, I put a latch on the door, so that's foiled him for a bit. Okay, so you've got a common k here, and then in the denominator, when you integrate this part, you are also going to get a common k. So that k is going to cancel in the numerator and the denominator, and then you will get your nice function e of theta, even though we don't know the maximum value here. Right, so that's something fairly important to deal with. So sometimes you don't even need the values of the function, right? In this case, we didn't need any values of the function. In this case, we didn't know the value here, but we had a few more specifics. We knew some numbers on this axis. And so we knew we had straight lines here. So just through one constant, we could get equations for our C of t. And then it contained an unknown, but because we only need E of theta, we don't actually care about the tracer itself. We are just using the tracer to get to the age distribution. And so when you stick it in this formula, that unknown constant actually cancels out, leaving us with E of theta, which is actually what we want. So that's maybe also to mention example 3, which also had something like that. So in example 3, again, we have a tracer function here. We don't know the maximum here, but we know that E of theta is going to have the same shape. So if you were to draw E of theta for that case, you have a 1 and you have a 1 and a 3 here. And we know it also has to be 0. So where C of t is 0, E must also be a 0. And then between 1 and 3, there's some other number here. So in this case, I'm just going straight to E. I'm not going to C. So in this case, I'm just looking at E of theta. So on the E of theta graph, again, we define a K. And this time, we take advantage of the property which we already listed here. So we said that the integral under E of theta must always be a 1. Now, if you look at this function, it's 0 left of 1 and 0 to the right of 3. So these areas are not contributing any area to that integral. So we might as well just integrate between 1 and 3. And between 1 and 3, E is nothing but K. So we can rewrite this as the integral between 1 and 3 of K in theta. So the rest of it in theta. And if you go ahead and integrate this, right, the integral of a constant is just K theta. And then we are going between 1 and 3. So 1, 2, 3. And so that's K times, and then this is going to be theta equals 3 and theta equals 1. So it's 3 minus 1, which is 2. So it's K times 2. And now we've got K times 2 equals 1. So simply here, K equals 1 over 2, 1 over 2. Right, so that's yet another example where we didn't know the number on this axis, but we are able to estimate it by taking advantage of the properties. So any questions or comments on that? Okay. So all those things we had discussed last time. So that's just kind of reminding ourselves there. And now we want to tackle a nice problem like this one. So let's read it. So it says here, a computational fluid dynamics study was conducted over a real reactor. And this apparently is the CFD result of that. So yeah, I would be quite disappointed if my CFD study gave me a picture like this. But anyway, when it says something like this, a CFD study, that's just trying to tell us that we know the velocity vector field. So if you look at that velocity vector field, you can infer some things about the nature of mixing there. And so here we can see in this thing that looks like something unmentionable here, it's actually trying to say that the CFD pattern is looking well mixed. So you've got a well mixed zone here. And then here you've got what looks like plug flow like behavior. And then you could question, well, what about this here? How do I interpret this? This looks just like another plug flow. So there's another bit of kind of visual notation here, which you need to be aware of, which is that the length of these arrows do matter. At least when I draw these pictures, I take these things to have a meaning. So when I draw a long arrow like this, right? So here it's got two heads, but they are joined. So by this, I just mean that there's one long arrow. So I'm trying to say with this one long arrow that this is a very fast stream. So this is basically bypass. So we don't regard what's happening here as another plug flow, that instead this is actual bypass. And that's important to say because actual bypass means that there's a zero time spent there. So it's not just that it's another plug flow part which has some space time. It's zero time spent there. So that's more specific. So we actually know the space time of this part. Over here, we don't know the space-time. We don't know how long the fluid is going to spend here. So, and yes, we do see this as a plug flow part, and then that as a CSTR-like part. So the way we would draw this is like so. So this is, let's do a different. So this is question, what, 5. So for question 5, the way we would draw this picture is to say we have part of the fluid that simply bypasses the whole reaction zone and exits. And then we have part of the fluid which first goes into a mixed zone here. Yeah. So there's a mixed zone here, and then there's a plug flow like part here. And then it's important to also show the direction of the flow. Oops. Right, so that's our understanding of what's happening from this computational fluid dynamics picture, right? And let's label some other things. We can say that we've got some real flow rate here. Let's call the real flow rate Q naught. And so the exit flow rate is also Q naught. And in this flow, some of it will split and bypass the reaction zone, and some of it will split and go down to react. And let's call the part that splits down to react, let's call the fraction of that beta. So there's beta Q naught going down this way. So then clearly going up this way is going to be 1 minus beta Q naught. So 1 minus beta times Q naught. Okay. And of course, as we said, we regard this as a bypass, as a pure bypass. So in a pure bypass, there's no volume. We regard all pipelines as having zero volume in comparison with the actual unit. So there's no volume here. So all the volume, the real volume occurs here. So the real volume, which we'll call V naught, the real volume is sitting in these two things. And let's call alpha the volume of the CSTR part. So this is alpha V naught. And by the way, if you do somehow have my solution, I don't know if I've used the same notation. I might have used the beta in the other place or something like that. So we're just doing this from scratch, right? So don't let that throw you if it's slightly different, if we've used different labels. So if all the volume is sitting here, then the volume of this part must be 1 minus alpha V naught. So the measurable things, the real things, right? Because this is, by the end of the day, some real reactor. It just so happens that we have this imperfect mixing going on, but this is a real reactor. So there's a real flow rate here, and there's a real volume here. So Q naught and V naught are those real known things. And then if you like, the virtual parts are the fraction of fluid going down here and the fraction of fluid going there. So I say that's virtual because it's not that it doesn't actually split, but we've defined, we've created a model. So this picture, this is our, if you like, our human view of what's going on here. This is our simplified picture of this real system. So therefore, this definition, the split, is fictitious, right? In the real world, there isn't actually a split between here and here. This is all one continuum. But our imaginary split in flow rate is this quantity beta. So beta is a fictional split. And there's no real way, in the real world, there's no real way to figure out what that split is, right? Well, actually, the whole of RTD is the way we do it. But I mean, if you just looked at even the CFD map, there isn't some kind of clear partition. It's not like in the real world, there's a distinct line that tells you, oh yes, if you're up here, then this is the bypass, and down there is the reactor zone. So beta is very much a virtual parameter. It's more like a conceptual parameter. So for us, in translating the real picture into our model of that real world situation, we use this beta parameter. And similarly, in terms of the volume split, you see, again, it's one continuous fluid here. There's no real partition between this mixed zone and this plug flow-like zone. We can imagine the difference between these two is some kind of wavy line that might be fluctuating and so on. So we are relying on this, there being some kind of virtual interface here. And so the real volume is split, and we have no way of estimating how big either zone is. But we need to, right, in terms of this model where everything is so explicit and clearly defined, we need to estimate the volume here and the volume there. So we've just labeled it alpha, right? We can easily go and label things in our own models. But when we look at this now, we have to figure out how to establish a value for that alpha. So of course, the way we'll do that is through the RTD. So we know that we are going to pulse tracer in, and we are going to measure the tracer at the exit point. And now we have to be able to interpret that profile that we get out. So we can sit there at the exit and get a C of T curve, and but what do we do with it? How do we interpret it in terms of these unknown things in our model? So I'm just going to copy this figure across. Okay, so that's our situation. Let's do our development here. Any questions or comments so far on any of this? Right, so we would like to interpret the signal that's coming out, and we can derive the equations. Maybe first, let's just imagine what we expect to happen. And of course, like we said with the earlier exercise, the way we would do that is imagine a pulse of tracer. So let's just imagine we have a pulse that we've pulsed in a bit of tracer here. And so we call the time of the pulse 0. So clearly, this pulse is just going to travel up here. So the pulse will also go straight through here and at the same time 0. Oops. So at 0, we've got the pulse moving through. And so you'll get the same pulse coming through at the exit here. But then when the pulse comes down here, first of all, that pulse is going to be exponentially decayed by the CSTR. In other words, the pulse that arrives down here, and yeah, we could draw it down here also. So the pulse also comes down this way, and then it mixes everywhere in the CSTR part. And so the CSTR will slowly release that tracer progressively over time. So it will exponentially release that tracer. So at time 0, we have tracer being released exponentially from that CSTR. And then that's the signal that's going into the PFR part. And I'm not sure if we said enough in the theoretical development that we regard a PFR as contributing a delay to any signal. So any fluid that attempts to enter the PFR, the PFR will just, whatever's coming through, it will just delay that whole thing. And so it will just time shift it by its delay. So everything that comes through here is just going to be delayed by the time there. And we can define the time here as tau p. So we know in the PFR part, there will be some space-time, right? Just as in the CSTR part, there's some space-time. We call tau s there. And then in the PFR part, we're calling it tau p. And now everything that comes in here is going to be delayed by tau p. So the stuff coming out here will look like this. So let's say 0 is here. And over here, the exponential decay had started from the 0, but now it's been delayed by tau p. So you're going to have 0, then you're going to have tau p here, and then your exponential decay will only appear after that. So it's going to do that. So the same signal, the same exponential decay will just be delayed by tau p. And so this is the signal that's now going up here. And so that signal is going to be added to this signal. And the result is going to be, you're going to get the spike coming through here. And then you are going to get also at tau p, you are going to get this exponential decay here. So those are the features that we expect to see, right? And in fact, it's helpful if you don't try to look ahead in the question. If just from that first CFD picture, you try to create the model and you try to anticipate what a pulse is going to do as it traverses the system. If you can come up with your expectation of an age distribution at the exit point, then it kind of tests your understanding when you look at what's given in the problem. And let's do that now. Let's page ahead. And you see that's, so in the problem, we go on to specify that this is what's observed at the exit. So at the exit, of course, we are measuring our tracer. And then let's assume now that, I'm not going to ask you every time to go and figure out E given CT. So just assuming CT was measured and we divided by the area under CT, then we got E of theta. So assuming all that was done in the problem, we are simply given that this is the result. So this matches our expectation here, right? So it looks like we are on the right track. It looks like our model that we proposed here is consistent with the observation. So this is, as much as you can use the RTD just to estimate the reaction rate and so on, It can also be used to understand or to test whether our understanding of the system is correct. So when we see a CFD picture like this, we've given some comments on how to interpret that picture, but there's still some doubt in our mind, right? We don't know if we've modeled the real world situation in the best possible way. But now we can see that according to the model we proposed, and that's talking about this network of reactors, in terms of that proposal, we are getting a result that is at least consistent with the measurement. So it looks like we have the right model there. Any questions or comments so far on that? Right now, the next step is to estimate these unknown numbers. So we said alpha and beta were these virtual parameters, and we would like to estimate numbers for them because then that would complete the model. Well, in fact, let's first talk about the model. Let's develop an equation that describes the system. So we can, it's useful to write a short text description. So we can say here, looks like the anticipated RTD matches the measurement. So we accept the model that there is bypass in parallel with CSTR in series with a PFR. And of course, in English, we don't really do this, but let's group this just so that it's clear. This is in parallel with this in series with this, and not CSTR is in parallel with this and it's all in series with PFR. That would be a totally different situation. So we'll bend the rules of English in this. Okay, so that's just a quick description of what we see. So we can say on the bypass side, so we can talk about an RTD on the top line and an RTD on the bottom line here. So we can say E bypass of theta, E bypass theta equals, and that's going to be the Dirac delta function. So delta theta, right? So we are saying here, right, we know the Dirac delta function. The Dirac delta function looks like this. The Dirac delta function is zero everywhere except at 0. So the Dirac delta function is 0, and then except at 0 where it's going off to infinity. Right, so that's how we define the Dirac delta function, and we're just saying Dirac delta of x. So we want the exact same function in this case, right? So to model this part of it where it's 0 here, and it's going off to infinity there, that means everything is concentrated in one instant there. It's Dirac delta function, just with the variable theta instead of x. So E on the bypass side looks like that. And then E on the reactor side, right? Because in effect, we've skipped out on the reactor part of that vessel. Then that's E of theta equals. And first, let's just write the CSTR part. So 1 over tau sub s. So we have to be careful to distinguish between the spacetimes between these two things. So tau s is the spacetime here, and tau p is the spacetime there. So 1 over tau s times, let's write it as x of minus theta minus theta over tau s. So that's what we would have if we had just the CSTR. but we know we also have the PFR part here. So there's going to be a delay by tau p. So we have an exponential function, and we want to shift that whole exponential function to the right by an amount tau p. And the way we do that is by just looking for the argument theta. So remember, theta tells you where you are along the x-axis. So if we just go and shift theta, then we'll accomplish what we needed to. So minus tau sub p. So we just shift the argument in theta. That's not the end of the story. We have to be a bit more careful because we've shifted it. That's fine, but if you consider values less than tau p, if you just use the exponential function here, if you put in theta equals, for example, tau p, then it's exp of 0 here, which is a 1. And we don't want this the exponential part here to be 1. We want this function to be 0, right? Because the function that we have here is only non-zero after tau p. Before tau p, it must be 0. Whereas if we just use the function like this, when we apply theta equals tau p, then we are here, and it will be exp of 0, which is 1. So we don't want a 1 here. We want a nice 0 for this part. So we want zeros here. So we just take this as a piecewise function. And so we say here for theta more than or equal to tau p, and this equals 0 for theta less than tau p. So, by the way, are you used to using the editor? So all these little shortcuts, you can also align this thing nicely. Align here, align here. Yeah, so learn these little shortcuts for writing your equations in Word. It gets quite easy after a while. You just have to learn a few of these codes for writing in your Greek letters and all that. Okay, so that's your piecewise function for E reactor. So we've got E bypass and E reactor, and then they both come together here, and then that's what we actually measure at the exit point. And now what we have to do is we have to join those two together, noting that there's a flow split here as well. So we can say E of theta, and in fact, what we should say is Q naught E of theta. So we are trying to count the volume of different areas. So what's the volume of fluid having age between this value and that value, right? So so remember E of theta delta theta. So E of theta delta theta. This is the fraction, right? So that's the fraction of fluid that's in a certain age range, in the age range theta to theta plus delta theta. And this, so that fraction times that volumetric flow rate, that's the volume in that age range. And that's E of theta is what we are defining as the age at this point here. So this is at the actual real exit point, right? These are just virtual flows. We created these flows, but that's an actual flow over there. In our original picture, yeah, in our original picture, we have a real flow here. These flows are virtual, but there's a real flow here. So here is where we are actually measuring our RTD. So so that is, we are so when we say E of theta, that's what we actually measure, right? Remember, our tracer is coming out there. So the picture we got here, this is the measured actual exit RTD. So now we are saying that the volume of fluid in that age range equals, and then we are going to get contributions from both these parts here. So it's going to be 1 minus beta times Q naught, and then times E bypass. So times E bypass of theta. And then we need to multiply by the delta theta. So I'm just going to cheat and copy this here. Right, so that's an estimate of the contribution from the bypass part to the age range theta to theta plus delta theta. So what volume of fluid is in that age range coming through here. Right, so that's there. And then we've got the remaining part, which is from the reaction side. So this is beta. Right, so coming through up at the bottom here, the fraction of the fluid is beta times Q naught, right? Beta times Q naught is coming up here, and then times the E of theta there. So that's E reactor part here. Right, so be sure you understand this step, right? This tells us how to combine our parallel streams. Any questions or comments there? Now we can see we can do some cancellations here. You can see Q naught appears in all these terms, right? There's a Q naught on the left-hand side, and Q naught is in both these terms. And then also you've got a delta theta here, a delta theta here, and another delta theta there. So Q naught and delta theta can cancel. So we can rewrite this as E of theta is nothing but the weighted sum of the E's from both branches. Right, so you just take E of theta in each branch and multiply by the flow split of that branch. So that's how we get E of theta. And so we can rewrite this as, this part we know is just delta theta. So this is delta, lowercase delta, and then E reactor is this piecewise function. Okay, let's just write it. Well, okay, so yeah, we can maybe, gets a bit messy here, but let's just do this. Let's put in, I'm just wasting time now. You can use this bracket thing here. So that's there, and then that's there. Right, so that's your age distribution. That's the model that we are looking for. Now, what we would like to do is figure out our values alpha and beta, right? Because once we have alpha and beta, we are basically done. We have a complete description of the whole system. Currently, there are some unknowns that are hidden here because this tau s, right, the space-time in the CSTR, that depends on this volume, and we don't know the volume of the CSTR. So that's because the volume is dependent on this alpha, which is an unknown fraction of the real volume. We also don't know even the flow rate passing through that part. And then similarly here, we don't know all these fractions. But we can, so that's the nice thing about the theoretical world. We can happily go ahead and define things as much as we like. So we like writing nice little labels on things. So we're going to write here the volume of the CSTR part divided by the volume through the CSTR part. We know that's equal to, and then it's going to be alpha times V naught. And then down here, it's going to be beta, and that's going to be Q naught. Right, so QS is beta Q naught and VS is alpha V naught. So that's the space-time in the CSTR. And then in the PFR part, we have the volume of the PFR part and the flow rate through the PFR part. Well, the volume we know is 1 minus alpha times V naught. And then the flow rate is the same as the flow rate through the CSTR. So that's also beta Q naught. So now we have tau S and tau P in terms of alpha and beta. Now, we could say, well, then those are some parameters behind here, and it's not so straightforward because there's a beta times all that. So anyway, we stick this, we can make a nice messy function in terms of the betas. So we can do that, and we can go ahead and fit. So we can play around with alpha and beta until it fits this curve nicely. So you can do that, that's fine. But we can also think about trying to be a bit cleverer than that. So can we find features on this graph that can help us get good estimates for alpha and beta quickly? And if you look at this graph, you can say, first of all, well, I can see clearly that my tau p is going to be 2.5 seconds, right? You can see this point here that we know the plug flow in the lower branch is going to do nothing but just delay the whole fluid by tau p. So this is clearly tau p. So we could just go ahead and say here, well, tau p is just 2.5 seconds. So we have a number for that. So now suddenly we have a relation, and V naught and Q naught, those are given to us with the problem. Let's just check here. 2.3 cubic meters and 0.5 cubic meters. Well, that's per minute. So 2.3 cubic meters. 2.3 cubic meters and 0.5 cubic meters per minute. So per second is, of course, that divided by 60. Right, so that's tau p. And so we still need alpha and beta here. Now for tau s, we can say that there's still one other feature here that we could think about. Let's go here. You might say, well, how about using some features from this nice spike? It looks nice and well defined. So it looks nicely defined, but you see, we can't really trust this point here. We don't know how high this point is supposed to go. And according to the theory, we know that's supposed to go off to infinity. So we don't trust this point. We won't try to use that. But this height here, this might be more controlled. And let's go and look at our model to see if we think this might be a more controlled point. So if you look at the model, you can see this part is going to be 0, right? So the Dirac delta function we said is 0 for any value where theta is not equal to 0. So at theta equals tau p, this part is going to be 0. So yeah, let's write it. Let's do it properly here. So we can say here theta equals, and I'm going to say tau p plus tau p. How do I? Let's say it like that. Tau p plus. So I'm saying tau p plus because it's a discontinuous function here, right? And by the way, this line in between shouldn't be there. It's supposed to be a proper discontinuity. So you've got 0 here, and then you've got some non-zero here. So if we just say tau p, it's not clear what value we are talking about. Well, in fact, actually, we've already made a decision. We've said when theta is more than or equal to tau p, then it's this. It's not 0. So in a way, we've already made a choice by specifying when it's equal to tau p, it's this and not that. But anyway, let's say we weren't too sure, that we just made a guess here when we put the equals there. Then just to make, if you like, just to make double sure, we will specify that we are going to take the point just to the right, which means definitely we are looking up here and not down there. Right, so we are looking here, and we know that this is equal to 0 there. So we can just knock this off. This is going to be 1 minus beta times a 0 over here. And then tau p plus obviously is the same as tau p. So this is going to be a 0. So this whole thing is going to be a 1 here. And now obviously we are not talking about theta less than tau p, and we made sure to stay away on the tau p plus side. So we don't have to worry about this lower branch. That's not where we are looking here. So we can just take this whole thing out and say this is nothing but beta times 1 over tau s. So it simplifies nicely like that. And now our tau s is going to be beta over alpha q naught. 1 over tau s is beta over alpha q naught over v naught. So it's beta times that. So it's going to be beta squared over alpha, and then it's q naught over v naught, q naught over v naught, q naught over v naught. Right, and then we can knock out the 0 here. We don't need to keep this. So that is what we will get for E on the theta, on the tau plus side. And if you look at it, we have a number. We can see it's 0.2 over there. So we can say that equals 0.2. Okay, so if you look at this, and just be careful with your units here. Remember, this is a distribution function. The area under this has to be 1. The units down here are seconds. So the units over here have to be 1 over seconds. So this is 0.2 per second. Right, so that's what, so we've got 2 relationships and 2 unknowns. So you've got this relationship and you've got this other relationship. And I'm just going to write that here. You've got V naught, oh, well, yeah, no, you have to keep that. That's V naught over Q. So that's the other way around here. So 2 relationships in 2 unknowns, and so you can solve it, right? Probably you would just take the alpha, you would solve for alpha here. So take alpha on this side and divide by 0.2 there, substitute for that alpha there. So you'll get a beta squared there, then multiply both sides by beta, and then you can solve that. So you can solve for alpha and beta in this case. Any questions or comments there? Okay, now if you look further in this question, you'll see there's what looks like a bit of a complicated description of the particles and so on. And that's because you actually haven't done the theory for this part. So this question was taken from a version of the course where I taught RTD right at the end, after I taught about particles and change in particle size and so on. So you will cover that kind of content later on, and actually with Dr. Lockhart this year. But for right now, let's just change this a bit. So let's say, so you can be given the kinetics in some way, and then you have to get conversion as a function of age. Just looking here, I think there was a comment just now. Well, how do I? Okay. So there's a question here. Could we use tau s as 22.5 minus 2.5 from the x-axis? Right. So the question is, if you look at if you look here, you're saying 22.5. Can you elaborate a bit there? 22.5, where does that come from? Is that the end value here? Yeah, so you see, this number at the end here doesn't tell you anything about how long this was just an arbitrary choice. I could have stopped the plotting at 10 instead of 22.5. So this difference between this end value and this value doesn't tell you anything about the space-time in the CSTR. And in fact, if you look at this curve, you can try and guesstimate what the space-time in the CSTR part would be. And the way to guesstimate it is to look for a value where you've got approximately equal area on the left and right. So I would say somewhere around here, maybe a value of 6. If you look at the area to the left of 6 here and a value to the right of 6, maybe those areas, or maybe it's closer to 5 actually. But you can see that the space-time in the CSTR is probably close to 5, not this number minus 2.5. That's going to be very far away. That's going to be about 20. So yeah, you can't easily you can't use the tail values to try and estimate the plug flow space-time. Yeah, that value doesn't actually have a meaning there. Does that answer the question? But maybe that it's a useful question in terms of reminding us that you can always get a quick guess about your average age if you look at your curve and try and estimate where's the point where my area to the left and the area to the right is approximately equal, right? So yeah, that difference, that point doesn't mean anything. So the difference between that and that doesn't help you get the space-time in the CSTR part. Okay. Okay, so that's how we get alpha and beta. And then the equation is fully specified. So if you come back here, we know we can substitute tau s and tau p, and then there's nothing left over in this equation that's unknown. So once we solve for alpha and beta, this equation is fully specified, and it fully describes your E of theta. So now what we want to do is estimate the average conversion. So when we think about doing or estimating the conversion across a reactor system like this, the first question is, what type of mixing do we have? And as I was saying, in this problem, we had particles, but it was kind of complicated. Let's take a simpler view. And in fact, we did this in some detail in the last tutorial. So we said if we have a first order reaction, we had that Ca equals Ca naught x of minus k theta. And then for the second order reaction, we had Ca equals, I'm just going to be guessing now, which I shouldn't do, but it was something like this. Yes. Sorry, 1 second, please. Apologies for that. Okay, so this was something like k times theta times, there may have been another Ca naught here. So just please check for that. And then what we had, or I think once you have Ca naught, then of course you can say X, the conversion of A in that particle or in that oil droplet and so on. That's 1 minus Ca naught, sorry, Ca over Ca naught, Ca naught. So in this case, it's simply 1 minus X of minus K theta. And in this case, it's XA equals, and in fact here, I think I'm giving you the XA version of this. So XA is 1 over that. I think it was that. So please double check. We did this, I know in the theoretical development and in the last tutorial, we did this in detail. So all you do is you solve the equation. So generally speaking, you take dc A dt. So you just write the batch equation for your individual oil droplet or your particle or whatever it is. You just write the batch balance. You solve that, and you'll get Ca as a function of theta, and then you use X is 1 minus Ca over Ca naught, and then you get conversion as a function of age. And so if we have conversion as a function of age, then we can say the average conversion is the integral. You probably think I really like writing the integral form all the time. X times theta. So that's how you estimate the conversion in the segregated case, right? We have E of theta. In fact, we have it in two forms. We have the graph. So with the question, we've got the graph. So we've got numbers on the graph already, but you can also use your equation now. And then the other side of it is X of theta. So you have your conversion as a function of age as well. And let's talk about that a bit more generally. So let's say you've got your E of theta graph here. So in this case, okay, let's draw the axes first. So your E of theta graph in this case looked like this. Okay, forgive that. And then you had the exponential die out here. So that's E. And then you've got X. So now obviously conversion is 0 initially. So you've got 1 minus, yeah. So your conversion is increasing with time, and it's going up to a 1. I must say this starts from 0, and then yeah, in this case it's going to do this. It's going to look like this. All right, so the first order reaction looks like this. So it's eventually going to go to complete conversion. So there's a 1 there and a 0 there. So your particle or oil droplet or gas bubble was not converted initially. And then as time went on, as that particle got older in the system, it became more and more converted. So it eventually went to 100% conversion. And then, in fact, all of them look like that. So for your second order reaction, it might be slightly different, and so on. So depending on your reaction order, you'll get some form like that. So you can solve the equation and get it like that, or it could just be given to you. So I'm not going to worry too much about the exact form of that. No. Okay, so I'm just going to say there's some function here, whatever it is. So let's just say we got some crazy kinetics and we had some function like this, right? So our conversion was varying with age like that. So now we want to perform this integration, and we can just do this numerically. So instead of applying the equation that we derived, and remember, and it's not that we are just throwing it away. The only reason we derived the equation was because that helped us figure out what the special values were going to be. It helped us interpret the data. So fine, we had a nice we had a nice graph here, but we didn't know what that 0.2 meant at all. We didn't know what that discontinuity meant. So we derived the equation, and then we were able to say exactly that was the relationship with that 0.2 and so on. So that's why we did that. But we don't need to use that model anymore, because we can just go ahead and use numbers for x of theta, because that's what's given here. So we can just come back to that graph. So we'll want the discrete form of this. So we can say this is the exact form, but we can also numerically estimate it as the sum. So let's just pull this part out. And we can say this is the sum over specific I choices of x, well, x at specific theta values multiplied with the delta theta, capital delta theta I, and this is times. So it's we're not talking about an operation anymore. It's an actual product here. So we will simply choose a set of values for theta, and we estimate a kind of mean here. So let's just say that there exists some mean value, and times delta theta. So if you take these two functions and multiply them together, let's do that. So if you imagine this, taking these two functions, and you take a value here and multiply by that, take a value there, multiply by that, you can construct a function, right? So here you can see you've got this value going off to infinity, but then you're multiplying by 0 here. Conversion is going to start at 0. So this whole thing will be 0 up to tau p. So you're going to get something here. Let's just produce this down. So so at this point, the product, and you can see that's going to start out high and go low. And then, so this is going to do something like this. Right, so just guessing here, and you should actually take numbers and multiply them and choose values here. So you can construct the product of these two. And then you can say, okay, here, I don't need to integrate before tau p, before 2.5, I don't need to integrate. There's a 0 contribution from there. Then over here, let's just take the approximate triangle here. And I'm not looking for you to spend a long time doing detailed integrations. Obviously, we can write code and do this to the nth level of accuracy. So don't waste time taking too many points here. Just take 2 or 3 or 4 points. And here I would say just approximating a triangle here, we can estimate the area. So the area under this function times delta theta, so delta theta, that big delta theta there, multiplied by the average height here, which is like halfway here. That's a good enough estimate for your average conversion. Okay, So that's how you solve those types of problems. Any questions or comments there? Now, the other thing I could have done is, instead of talking about a segregated fluid, we could say, well, we don't need the fluid to be segregated. We don't need these to be particles or oil droplets or gas bubbles. This could just be a continuous fluid that's reacting here. So if that was the case, if the reaction was actually homogeneous and not heterogeneous, and please do watch those videos carefully about the differences between micromixing and segregation, right? So segregation is when all your reacting fluid is in discrete lumps, right? In distinct bodies of fluid. So the reaction might be in the particle only, or it might be an oil. So that's a segregated fluid. And so everything we've described here is for a segregated fluid. You use this approach if the fluid is completely segregated. So each thing is its own little batch reactor. That's totally different to the case where your fluid is homogeneous. So if this was all a gas phase, you could still have a well-mixed zone here, plug flow-like zone here, and a bypassing here. So if it's a homogeneous fluid instead, then it's not the same. You can't use, number one, you can't use the segregation model anymore. This doesn't apply for a homogeneous fluid. But you can still simply think of it as a network of reactors. So the same network that we've proposed here, we would say, well, we've done in the first few weeks of the course, we've already talked about CSTR in series with PFR and all of that. So you could simply develop the material balance using a homogeneous fluid style approach. So you could say for the PFR part, right? You can say the concentration in the PFR follows this balance: DC maybe A, DC A, D tau. That's equal to RA. And in fact, here we need to be a little bit careful. We need to say the concentration in the plug flow part is going to be the reaction rate in the plug flow part. And let's say it was a first order reaction, then that would be K, minus K times CAP, right? And then for the CSTR part, we would say D, well, for CSTR, we use X times FA naught equals RAV. And here again, we need to be careful. So we would specify it's the volume of the CSTR part, and it's the conversion in the CSTR part. And FA naught would be the molar flow from the PFR. So it would be the volumetric flow rate times beta times the concentration, which would be CAP. So this would be the molar flow from the plug flow into the CSTR. And so we would solve these two balances. And now you see you can do it because, oh yeah, here, yeah, that's fine. So here we can solve these balances because we've gone and found alpha and beta. So the alpha and beta we discovered here still applies in this case. So in the case of a homogeneous fluid, it's still the case that we've gone and figured out what the flow splits and the volume splits were. And then we just go ahead and think of those as this is just going to be a balance on a homogeneous fluid. So please understand this point carefully, the difference between regarding it as a segregated fluid and a homogeneous fluid. The homogeneous fluid we've dealt with in detail in the first part of the course. The segregated fluid, that's where the reaction is happening in these little groups. And so you have to then introduce the segregation style model. Any questions or comments there? And that's basically all I wanted to go through today. So this is, in effect, the last chance to in person talk about any questions or comments. All right, so that's basically it from me on the course. Yeah, RTD, it's an area that always interests me from the first moment, right? From my first attending of a course like this, I was taken by this RTD concept, and it stayed with me over all these years. I've contributed to the field, so I found a solution to unsteady state RTD, and I might put out a video about that. So it's something that I always enjoyed working with, and I also it somehow always comes back. So even in my research, somehow RTD always follows me back, and I always enjoy it. I always like working with RTD. And besides just liking it because it's like an interesting puzzle, it's a tremendous step forward in the types of reactors we can model. So you can see, like in this case, it was a very complicated situation. If you look at this type of mixing, you can just throw up your hands at this point and say, there's no way for me to predict what's going to happen in this reactor. Whereas we broke it down, and we now that we have this tremendous power of RTD, we can actually find the flow splits, the imaginary flow splits and volume splits. We can actually get numbers for those, and we can then actually predict precise numbers and actually predict what the conversion is going to be from this reactor. Whether it's micro mixed or segregated, we can still estimate what's going to happen in that reactor. So I was just blown away by the fact that you could do this, and from such a simple method, right? Just pulse in a little bit of tracer here, measure concentration there, divide under the area, and suddenly you've got the RTD. It's as easy as that. It's a wonderfully simple thing to do, and you totally avoid CFD studies and all that. And I've done projects in research where we used CFD extensively. In fact, just in this last graduation, one of my CFD students graduated with his PhD. So we've done a lot of research in this area, and I use CFD now and then. But the fact that you can get away from all the work, and there's a lot of work to do to get CFD working properly. It's almost a cheat. Sometimes I think of RTD as a cheat. The fact that you can totally avoid this whole computational fluid dynamics and just pulse a little salt in here, measure a little thing out there, and suddenly you can predict precisely how this reactor is going to perform. It's really a wonderful field, and so I hope, I know things are busy and it's hard for you to appreciate this field. So I hope you do find a space to spend some time thinking about this, because it's one of those things that there are still unsolved problems and there are still interesting areas to pursue in this field. Okay, so that's it from me for the course. Of course, please go ahead and email me any questions and things that you have. I know there are some admin-y things to take care of. We'll sort that out. So thank you very much, and I'll see you probably next year in the process dynamics and control course. Okay, that's it. Thank you.